Hello everyone, my name is Alessia. I am a PhD student at the University of Verona, and today I'm excited to share some insights from my research in neurocognitive science, focusing on how the brain processes sensory information. Well, our brain interacts with the world through our five senses and processes these inputs through specific functions at different levels from perception to awareness. Each of these processes is linked to distinct networks of brain areas. For example, visual information processing starts in occipital regions at the back of the brain, and we can collect proof of it by recording neural activity using techniques like electroencephalography or EEG. But what happens when one of these sensory systems, like vision, is compromised? You might think that once a person loses his ability to see, that is to say that he completely loses his ability to visually perceive the external world, the brain regions responsible for vision would stop functioning. However, the brain doesn't simply shut down, but it adapts, demonstrating a remarkable flexibility known as neural plasticity. Well, my work specifically investigates how brain copes with the vision loss due to retinal dystrophies, a group of inherited eye disease that damage the photoreceptor cells in the retina, namely rods and cones. These cells are crucial for detecting light, and as they deteriorate, the ability to perceive brightness, colors, and contrast is highly reduced. Also, affected individuals gradually lose their sight either from the center outward or from the periphery inward, depending on whether rods or cones are affected first. All these irremediably compromise the capacity of patients to respond to visual stimuli and navigate their environment. This progressive sight loss impacts not only vision itself, but also how the brain processes sensory information in general. Previous findings show that the brain doesn't remain inactive, but it continuously seeks a way to optimize its function. Even in the absence of visual input, the brain's visual areas may adapt by enhancing other senses like hearing or touch, or by preserving some level of neural activity for visual stimuli processing, especially when they are silent and very easy to detect. This last aspect represents the central question of my research. Does the brain still process visual information, and if so, how? To explore this, we use non-invasive tools like EEG, transcranial magnetic stimulation, or TMS, and a passive visual task. TMS allows us to modulate brain activity painlessly and temporarily using magnetic fields. Using it combined with EEG, we can measure brain responses and determine whether the visual areas are still reactive to externally induced stimulation. For patients who retain some vision, we employ visual tasks using specific and customized visual patterns to trigger brain responses. We use EEG to track brain activity in response to a flickering high contrasted stimulus. The results obtained in our pilot study conducted on healthy participants are promising and confirm that our approach is effective to elicit and detect cortical visual responses. And we can say that now we are finally ready to apply this method to patients with retinal dystrophies to investigate whether their brains can still process some kind of visual information even in advanced stages of vision loss. With this research, we want to expand our understanding on how the brain adapts to gradual loss of a key sense, shedding light on the broader topic of brain plasticity. For individuals affected by retinal dystrophies experiencing vision loss, this research could open up new possibilities for efficient treatment or rehabilitation, including development of visual prosthetics, contributing to improving the quality of life and helping them maintaining greater independence. Thank you for your time. Thanks for this amazing team for its support, and simply bye bye.